Have you ever stopped to think about the incredible variety of sounds all around us? From a tiny whisper to a massive guitar solo, every single sound has its own personality. Well, today we're going to be detectives. We're cracking the sonic code to figure out what gives each sound its unique voice. So let's start with a mystery. Picture this, a guitar and a piano. They can both play the exact same note. Let's say it's a middle C. You can play it at the same volume, it's got the same pitch, but you'd never, ever mistake one for the other, right? So what's the secret sauce? What's that invisible difference our ears are so good at picking up on? That's the puzzle we're gonna solve. And believe it or not, the answer, at its very core, is a wave. See, sound is just energy. It's created when something vibrates, and those vibrations travel through the air in waves that our ears pick up. The entire secret to a sound's identity is hiding right there, inside the properties of that wave. Okay, so let's get our investigation started. We're going to put these sound waves under a microscope, metaphorically speaking, and really decode what makes each one special. It turns out every sound can be broken down into three main clues. First, there's its loudness, its raw power. Then there's its pitch, that's how high or low it sounds. And finally, there's its quality. This is the really mysterious one. It's like a sound's unique fingerprint. We're going to tackle each one by one. All right, first up, let's talk about the most obvious one, loudness. What's actually happening on a physical level that makes one sound a whisper and another one a shout? Well, the answer is a property called amplitude. Now, I know that sounds super technical, but trust me, it's actually pretty simple. If you think of a sound wave like a ripple in a pond, the amplitude is just how high that ripple is. It's the size or the intensity of that wave. This slide shows it perfectly. Take a look at that top wave. See how short those peaks and valleys are? That's a small amplitude. That's a soft sound. Now, look at the bottom one. Whoa, it has this huge amplitude with really tall peaks and deep valleys. And that, my friends, is a loud sound. So the key takeaway here is super simple. The bigger the wave's amplitude, the more energy it's carrying, and the louder the sound we hear. It's really that direct. And we measure all this loudness in units you've probably heard of, decibels. And this scale really puts it all into perspective. A whisper? That's about 30 decibels. A normal chat is double that, around 60. But a police siren at 120 decibels, that's literally painful to our ears. And a rocket launch? Well, that's just off the charts. The range of power is absolutely incredible. All right, clue number one, loudness, is solved. Let's move on to our second clue, pitch. This is the thing that lets us tell the difference between a deep bass note and a high, shrill whistle. The secret behind pitch is something called frequency. Now, if amplitude was the height of our pond ripple, frequency is all about how fast those ripples are happening. It's the number of vibrations that occur every single second, how fast or how cramped together they are. And this visual just explains it perfectly. Check out that top wave. It's all stretched out, kind of lazy, right? That's a low frequency, which our ears hear as a low pitch. Think of a bass guitar. Now look at the bottom wave. It's way more frantic. The waves are all squeezed tightly together. That's a high frequency, and we hear that as a high or even shrill pitch. So just like before, the rule is really straightforward. The faster the vibrations, meaning the higher the frequency, the higher the pitch of the sound we hear. Simple as that. Okay, this brings us to our final, and honestly, the most crucial clue. This is the one that's going to solve our original mystery about the piano and the guitar. This is the characteristic known as quality. So let's go back to our big question. We know loudness comes from amplitude, and pitch comes from frequency. So if a piano and a guitar are playing a note with the exact same amplitude and the exact same frequency, what else could possibly be different? I mean, what's left? The answer, and this is so cool, is the shape of the wave itself. Look at this. The top wave is from a tuning fork, and you can see it's really pure, simple, and smooth. But the wave on the bottom, from a piano playing that very same note, is way more complex. It has all these other little waves mixed in, creating this jagged, totally unique pattern. That specific shape is the sound's fingerprint. And this fingerprint actually has a name. It's called quality. Or sometimes you'll hear the fancier word for it, timbre. It's the one thing that lets us tell two sounds apart, even when they have the exact same pitch and loudness. And it all comes down to the wave's unique shape. And with that, we have all three clues. we've officially cracked the code. So let's put it all together one last time.
So the secret recipe for any sound is this combination of three things: the wave's size, its amplitude, that gives us its loudness; the wave's speed, its frequency, that gives us its pitch; and the wave's specific shape, its form, that gives us its unique quality, our timbre.
And that's why a guitar sounds like a guitar and a piano sounds like a piano. They're just physically built in a way that produces sound waves with a different, characteristic shape. It's the unique mix of loudness, pitch, and quality that gives every single sound in the universe its own recognizable voice. So the next time you're listening to music, or you hear a bird singing, or even just the sound of someone's voice, you'll know what's really going on under the hood. You're not just hearing a sound, your brain is decoding a complex wave of information. So now that you know the code, what sound are you going to really listen to first?